sign. Okay. All right. Here we go. Thank you very much, Dale, for inviting me. This is a pleasure. As Dale mentioned, this is kind of a pet project. I've always been interested in floods, typically more contemporary floods, floods that occur in the present day world. And this is an example of one that kind of blends my interests in contemporary flooding and glaciation, the last ice age. And I got started on this, well, geez, if I really look back to when I got started, it was when I worked for the Geological Survey of Canada, because I was mapping in central BC. Although others had previously published reports that there had been a glacial lake in that part of the province, I really began to document it in a lot of detail. And it was as I'll show you, it was the largest lake glacial lake that formed as the ice sheet was wasting away. It was the largest in British Columbia, quite a giant, and a really interesting story around it. However, that work was done in the 80s, and that was before we had this really marvelous technology called Lidar. And I suspect most of you are aware of Lidar technology. It really is remarkable, and it shows you how much technology is driving science, whether it be earth science or medicine or physics. Technology is a real driver for technology, for science. And Lidar is so cool. I can't tell you, it's just so cool. I wish I had had it when I was mapping in the 80s, but it didn't really come on board until the new millennium. And what it is, and it can be operated from the ground, but the Lidar imagery that we typically use is acquired from aircraft. And the aircraft is equipped with a sensor that's an active sensor. It allows a pulsed Lidar, or a pulsed laser beam to be emitted from the aircraft, from this instrument, down to the Earth's surface. And the beam reflects on anything at the Earth's surface. And as the aircraft moves forward, of course, you get a swath of these beams moving across the landscape. And individual light waves will reflect back on everything they encounter. So vegetation, structures, the bare earth. And it's the bare earth that we really are interested in. So there are computer software programs that allow you to strip off everything but the waves that are reflected off the bare earth itself. It basically strips all the vegetation off and gives you an image of the Earth's surface, complete with elevations, precise geographic locations. It's a false image in a way, but it's an image that only a geologist could love, because it provides a beautiful, beautiful representation of the landscape. And I want to just give you an example, because I'm going to return to how we use this technology, Lidar imagery, to begin to better understand this megaflood story. So this is an example of a conventional satellite image. And I just picked one at random where I had Lidar imagery. But this is a satellite image of an area that was covered by the Cordilleran Ice Sheet. You can see where it is in the province of British Columbia. It's right in the center of the province. It's an area called Summit Lake. And just one sec, I'm going to get a laser pointer. So this road up here is Highway 97, which takes you to the Yukon Territory in Alaska from Prince George. And this is partly deforested, this terrain. It's naturally forested, but you can see there are areas that have been logged or deforested within the past 40 or 50 years. And you vaguely see landforms on that. This here is, I think it's a high hydroelectric line. But if you produce a Lidar image from an aircraft, this is what it looks like. If you strip all that vegetation off, this is what it looks like. And you see these landforms in this glorious detail. So you can see, for example, up here in this right-hand corner, these are eskers that formed beneath the ice sheet when it covered this area. You can see this very, very large old meltwater channel. There really is no stream in it today, but at one time this carried a huge flow of water. There's another lower channel over here. You can also see this ridgy topography here. It almost looks like rock outcrop, but these are really glacial streamline forms. These are drumlinoid ridges that were formed as the ice flowed transversely across this landscape in this direction here. So wow, when you just go back and look at that, that's what I was dealing with when I was mapping this geology in the 80s. I surely wish I had had this, because it's like I can see this topography and interpret it in tremendous detail. And it's really this enhanced imagery of the Earth's surface that allowed me to really get a grip on this flood story, because British Columbia is largely forested. There is some grassland areas where you can see these landforms with aerial photographs and with satellite imagery, but much of the province is covered by forest. And it really does impede a geologist from interpreting the landforms that you can see on the Earth's surface. So this is really a story in two parts. And this story begins near the end of the Ice Age, so the end of the Pleistocene. Roughly about 17,000 years ago, as recently as that, this entire area was covered by an ice sheet. British Columbia was covered by an ice sheet called the Cordilleran Ice Sheet. And this ice sheet extended westward out onto the continental shelf along the Pacific Ocean shoreline. It extended into northern and into central and southern Yukon. And it was connected with a coalescent mass of glaciers, which we really think of as part of the ice sheet in the Alaska ranges and the other ranges in southern Alaska. Of course, it also extended down into the northern states, into Montana, northern Idaho, and Washington state. And this was a big ice sheet, but actually, when we look at it in the context of ice cover over North America during the last ice ages, it's 17,000 years ago, it seems fairly small, because we had this much, much larger ice sheet burying much of northern North America at the end of the Pleistocene that we call the Laurentide ice sheet. My focus, however, I'm a mountain type of guy. I like working in mountainous terrain. So I've always worked in British Columbia and the Yukon, and my focus has been on this montane ice sheet, the Cordilleran ice sheet. And I like to use analogies to illustrate, if I could be a fly on a wall, what I'd see in British Columbia if I could teleport myself back 17,000 years or so. And this is what it would look like. I'm, of course, using Antarctica as an analog, but all of British Columbia was buried beneath up to about 3 kilometers of glacier ice that I mentioned before. It flowed in a complex pattern controlled by the topography on which it rested. And these lines here, these light blue lines, show the direction that the ice sheet flowed at the last glacial maximum about 17,000 years ago. There's a little bit of an inconsistency down here. Really, we think all of Vancouver Island was covered by the ice sheet. And of course, the Puget Lobe extended down through the Puget Trough past Seattle to Olympia, Washington. So this is what it looked like. Remarkable. You know, to me, I got into geology because I could hardly believe that only 17,000 years ago, you know, the northern part of the continent of North America looked like this. And it's just really a remarkable story, in my opinion. And people, you know, when I give the talk to an audience that knows no geology, they say, well, 17,000 years ago, I mean, that's like the beginning of the Earth, but it's not really. You know, we know the Earth is much, much older. It's 4.6 billion years. So this is a drop in the bucket of geologic time. And to me, it seems like yesterday. Wish I could be a fly on a wall to actually have seen what it looked like. So the story here that I'm telling you has two chapters, returning to these ice sheets. The first chapter is really the first intimation that there was a megaflood that extended down the Fraser River Valley to the present location of Vancouver and probably Bellingham as well. And this is ocean drilling program cores that were collected from Saanich Inlet. And I'm going to spend a few minutes talking about that study, which dates back to about the turn of the millennium, about the year 2000. And at that time, I had a PhD student, or oops, what did I do? Sorry. I think I lost my screen there. There, sorry. I was co-supervising a PhD student who works for the Geological Survey now. Her name's Andre Blaise Stevens, and she was involved in an ocean drilling program leg in Saanich Inlet. Saanich Inlet is it's a fjord, you know, a glacial fjord, really, probably the southernmost fjord in British Columbia that indents the southern tip of Vancouver Island.
Say, John, we're not seeing your screen. Yeah. John, we lost your presentation screen.
Uh-oh, okay, hang on. How did that happen? Let me try that again. Okay, are we back on?
Got it.
Okay. Sorry about that. I had no idea how that happened.
John, go ahead and put it into presentation mode, please.
Okay. So Saanich Inlet indents southern Vancouver Island. And the ODP ship, the Joides Resolution, acquired a series of cores from two sites, site 1033 and 1034, which are located in the map at the lower left. And I should point out that this is pretty far from the area of Vancouver, the metropolitan area of Vancouver. It's about 40 miles or 70 kilometers, something like that, away from Vancouver, which carries some significance. So these cores were quite long. They extended through a very thick post-glacial sediment fill and basically bottomed out in sediments that date to the time of the last glacier occupation in the area. And this is just a brief summary of the cores. And just to explain, the post-glacial part here is shown in the gray toned pattern. And there are 3 cores that are shown here from one site, site 1033, and 4 cores that were collected from site 1034. And they're pretty close to one another. So one would expect them to have very similar stratigraphy or sediment sequences. But the cores themselves are up to 70 meters long. These are very, very long cores. And as I say, they bottom out in glacial sediments, which are here shown is basically in white. GMM is glacial marine mud. And the laminated mud part, the organic mud part of the sequence is rather monotonous, actually. It's very similar and dates back to about 12,000 years and records the gradual accumulation of just normal organic rich muds, or gycha, in the inlet. But there are 2 anomalies within the sequence at depths of about 50 to 60 meters, 50 to 70 meters, that is, depending upon the core. And they're shown here by these red bars. They're quite thin, but they are distinctly different from the laminated mud sequence. They represent gray, olive gray, silty clays that consist of entirely of inorganic sediment that are really anomalies in this 12,000 year sequence of sediments. The numbers there on the right of each core are radiocarbon dates. They give you a sense for the age of the sediments of these anomalous beds. So if we take a look at them, at those beds, this is what they look like. You can see in that left part of the photo is a blow up of one of these gray beds, these distinctly laminated silty clays that differ from the laminated muds, the post-glacial muds, in having no organics. And they represent, really are concentrated in a sequence of sediments that spans about 1 meter of these 70-meter cores at depths of sediment that date back to about 11 to 12,000 years. And an interesting thing about these sediments is they contain exotic fossils, exotic microfossils. So this is a collection of some of the exotic spores and pollen that are widespread in these anomalous gray silty clay beds that you do not find anywhere else in the post-glacial sequence. And just to give you a sense for what these are tertiary and late Cretaceous plants. They're the spores and pollen of tertiary and late Cretaceous plants. Cedrus is true cedar. We don't have true cedar. We have western red cedar on the coast today, but true cedar is a foreign plant. Osmunda is a spore, as is Glacial. They're both tertiary spores. Pterocarya is what we call the wingnut. Liquid ambar is sweet gum. Ulmus is elm. Carya is hickory. And Tilia is linden. And the two at the lower right, the bottom right, are, well, one is a Paleocene pollen grain, and the one at the far right lower corner is a late Cretaceous pollen grain. So why is this significant? You do not get tertiary rocks on Vancouver Island, at least you don't get tertiary sedimentary rocks on Vancouver Island. Rather, you get them in the Bellingham area, the Chuckanut Formation, and you get them around Metro Vancouver, extending eastward out into the Fraser Valley. They're shown here by the dark gray pattern. These are the rocks from which those ancient spores were derived. And so somehow you've got to transport those spores and pollen grains from their source to the east of Saanich Inlet, and Saanich Inlet is located right down here. You have to get them across what is now the Strait of Georgia and into this fjord on southern Vancouver Island. And in this paper, Andre Blais-Stevens argued that the anomalous nature of those gray silty clay beds, together with the pollen composition of the microflora, indicated that they were probably transported by a rare event, and she attributed it to a large flood that would have crossed the Fraser Lowland. So that kind of was published back in 2003 and really got me thinking about, okay, what is the source of that flood? If it indeed is a flood that transported the sediment that far across what is now a marine waterway. So that basically created a bit of a hiatus in the story, because I didn't really pick it up until a colleague from the University of Northern British Columbia, Brian Menounos, and I were able to mount a Lidar survey of the Fraser River Valley. So by about 2015, we had the capability of actually acquiring Lidar data of the Fraser Valley to test whether there's any evidence in the landforms, in the geomorphology, to support the notion that a flood traveled down the valley and across the Fraser Lowland, bearing in mind that there could be other possible sources for the flood. But in the back of my mind, I was pretty convinced that Glacial Lake Fraser was the source because it was the largest body of water that could release and produce a flood of the size that would transport sediment into Saanich Inlet. So that's basically where we're going now, is the second chapter in this story, looking at Glacial Lake Fraser. And to do this, we have to kind of introduce the question of when this flood possibly could have happened. Now, if we assume that it was from a late glacial lake, that constrains the story to after 17,000 years ago, because that was the time when the ice sheets, the Cordilleran Ice Sheet and the Laurentide Ice Sheet, achieved their maximum size. And at that time, the two ice sheets were stitched together along a margin that extended from southeastern Yukon down to, well, we think probably down to the Calgary area. This may be an older representation of the length of the suture between those two ice sheets. But we know for sure that those two ice sheets were confluent along their margins at the last glacial maximum around 17,000 years ago. So I'm going to show you a series of snapshots in time as to how the ice sheets separated and eventually disappeared, and the time frame over which that happened. Oops, sorry. So by 15,000 years ago, the Cordilleran Ice Sheet was beginning to pull back on its western margin, and in Washington, Idaho, and Montana, it was beginning to pull back a bit. And also the Laurentide Ice Sheet was beginning to thin along its western margin and reducing the suture zone between the two ice sheets. And as that happened, a series of lakes formed along the western margin of the Laurentide Ice Sheet and evolved over time. And they formed there because the natural slope of the land is down towards the east in the prairies. You know, the land, once you get east of the Rocky Mountains, we have the interior plain, which slopes gradually towards Hudson Bay and the St. Lawrence Valley. And so lakes, if they're basically, or water, if it wants to flow to the east, is unable to, so it accumulates in glacial lakes. And these lakes are really quite interesting in terms of the history of the Laurentide Ice Sheet. In British Columbia, it's not so obvious here, but highlands were beginning to emerge from the ice sheet as the ice sheet thinned. So it was not only pulling back, but it was also thinning over its vast interior area. And this continued, of course, with time. And by about 14,000 years ago, maybe a little earlier, the two ice sheets had separated. Both ice sheets were still very large at this time, but they had separated, and glacial lakes were expanding and evolving as the Laurentide Ice Sheet pulled back towards the east. By 13,000 years ago, the ice sheet, at least the Cordilleran Ice Sheet, was much diminished. It was getting to be on its last legs, you could say. So areas at the periphery were now ice-free, including the Puget Lowland. Much of Vancouver Island was ice-free. Ice had retreated off the continental shelf, and very large areas were appearing as ice-free areas at moderate elevations in the interior. Here shown by these splotches of white. And interestingly, by 11,000 years ago, the Cordilleran Ice Sheet was history. It did not exist after 11,000 years ago. And we know from work that's been done throughout our mountains that glaciers by 11,000 years ago in British Columbia were no more extensive than they are today. Now, this wasn't the case with the Laurentide Ice Sheet. The Laurentide Ice Sheet persisted for another 5,000 years, and its final demise didn't occur until about 6,000 years ago over parts of Labrador. And so there's a big, long history of glacial lake evolution, of resurgence of lobes of the Laurentide ice sheet that basically happened well after British Columbia was deglaciated. So taking that story into account, you can see that if Glacial Lake Fraser were to contribute to a flood that could explain the Saanich Inlet core record, it would have to be in a fairly narrow time window before 11,000 years ago, because there would be no way that that glacial lake could have persisted once the ice was totally gone. So it really has to date to that time when ice is beginning to evacuate over the interior of British Columbia, but probably there still was dead or dying ice lobes in the valley that could have impounded lakes. And we know these lakes did exist. A good example, again, an analog situation would be up in the Alaska Panhandle area. This is actually from British Columbia, but very close to the Alaska boundary, where a very, very large glacial lake, now it's almost 30 kilometers long, has formed during the current warming period since the early 1900s. This is Glacial Lake Melbourne. And I kind of think that this represents a fairly good analog of what our interior BC valleys, our intermontane valleys, could have looked like during this short period when the Cordilleran Ice Sheet was dying, was basically on its last legs. And we know this happened. We find glacial lake sediments in most all our interior valleys. If any of you have driven through the South Thompson Valley, east of Kamloops, or even west of Kamloops, you will have seen these very famous white silts that George Dawson wrote about, 150 years ago now. These are benches of glacial lake sediments that have been eroded, in this case by the South Thompson River, after the glacial lake in which those sediments were deposited disappeared. And we know that this happened, that particular lake, Glacial Lake Thompson, disappeared about 12,000 years ago. So this is the situation that we see in almost all our interior valleys. It's very, very common throughout British Columbia to find glacial lake sediments in the valley bottoms or close to the valley bottoms. And as I said, one of the largest of those glacial lakes, the largest we think in the province, was Glacial Lake Fraser. It was dammed by ice that still extended out from the coast mountains here. These are our highest mountains, really, our highest and most impressive mountains. And during deglaciation, as this interior basin was becoming ice-free, there was still ice extending across what is now the Fraser River and forming a dam that impounded this huge, huge glacial lake that extended more than 100 kilometers to the north, backed up into the Rocky Mountain Trench into what we call the Robson Valley, and extended westward to and past Vanderhoop, a community that's about an hour's drive west of Prince George. So very, very large lake. You can imagine it held a tremendous volume of water. So this is the situation immediately, I think immediately prior to the megaflood. We think that this glacier dam was breached by continued downwasting and retreat of glaciers flowing eastward across the interior plateau from the coast mountains. Eventually that dam weakened to the point that it failed catastrophically. Sounds very much like a Glacial Lake Missoula story, and it is. You know, it's an ice dammed lake that failed catastrophically. So I would just like to show you a few LIDAR images. We're turning back to LIDAR, and this is near and dear to my heart because I mapped this area using aerial photographs back in the mid-'80s. But if I had had LIDAR, I could have said a lot more about the glacial story, because you can see these beautiful, beautiful drumlins or drumlinoid ridges that are shown here in the red and orange hues that record ice flowing from lower left to upper right when this area was covered by ice. And ornamenting those or etched into those are those red lines, beautiful shorelines of Glacial Lake Fraser as it gradually lowered through this period of deglaciation. So each of those red lines is a little beach line. And the blue area to the right is not water. That's actually the city of Prince George. City of Prince George sits on terraces of the Fraser and the Chaco River, inset into this topography to the left that's higher. So that lake basically covered all of the Prince George area. You can see where it is here. The blue area on this upper image is the area that was covered by Glacial Lake Fraser. And we're basically looking at the terrain at the city of Prince George. So wow, every time I see Lidar, I just get really excited as a geomorphologist. And turning into the area of the Rocky Mountain Trench, the Robson Valley, this is a color enhanced Lidar image tilted up to show these beautiful shorelines on the valley, on the rising slope of the Rocky Mountains that allow us to map out the extent of this lake and to document its successive lowering over time. And we also have a good sedimentary or stratigraphic record of this lake. This is an example in that same area, a little farther north, of very thick lacustrine sediments. You can see they're vaguely bedded, but they're lacustrine sediments deposited on the floor of Glacial Lake Fraser when this area was flooded. So this map is a little busy, but it shows the situation, the extent of Glacial Lake Fraser when the ice dam failed. Now that happened when the last shoreline was occupied at about 740 meters elevation. That's about 2,300 feet. So it's below that suite of strand lines that I showed you in the last images. But when the lake had lowered to 740 meters, that dam failed. The glacier dam failed, we think, and produced a downstream flood. Now this flood traveled down a canyonized valley. If you think about analogs like Glacial Lake Missoula, it's not particularly a good analog because the floodwaters were confined to a valley, a narrow valley, whereas Glacial Lake Missoula floodwaters spilled over the Columbia Plateau. Admittedly, they were channeled down the Columbia River Valley beyond as it flows westward towards Oregon, towards Portland. It was confined in a valley there. But over this entire 200-kilometer distance from Williams Lake, which is where the dam failed, down to Hope, where the floodwaters exited the Fraser River Valley, Fraser River Canyon, it was a canyonized valley. So we do get the same types of flood-like landforms, but the topography that the floodwaters traveled across was very different from Glacial Lake Missoula. Okay, so stepping back a bit. So before I had this Lidar imagery, I would travel through the Fraser River Canyon, up through past Hope, Yale, Lytton, and just south of Lytton, as I was driving along the Trans-Canada Highway, I would look off to my left and see this magnificent exposure, you know, that you can see along the Fraser River. It's about 100 meters high. One of the national rail lines is right at the bottom of this image, and the top is about 100 to 110 meters, or over 300 feet higher. And I kept looking at that and I said, you know, I'm a glacial geologist, but I don't really understand what I'm looking at here. I mean, these are weird sediments. You see they're gently inclined, they're continuous beds, and you get these very large boulders up to 2 meters across, kind of punctuating otherwise finer sediments, sands and more gravelly sediments. And over time, as I did my own studies with PhD student in on the kind of channel scabland in Glacial Lake Missoula, I came to recognize these as being diagnostic flood sediments. They really represent you know, a major flood that can transport large amounts of sediment on a planar bed in deep water, moving in a sort of a hyper sediment concentrated state, large boulders scattered through it. So I was pretty convinced that I was looking at eventually, you know, after driving by here 20 or 30 times, that I needed to go over there and really look at this stuff because it's on the other side of the river and it's not the easiest place to get to, surprisingly. But eventually I did. And what really triggered that was the Lidar image. So this is the same image on the bottom of these dipping flood sediments, but we have the Lidar imagery that tells us what the surface looks like, the barer surface. And what you're looking at, that above the line labeled B, which is where the photograph is taken, is sort of a whaleback form. You know, it lies down valley of a bedrock ridge that kind of extends out into the Fraser River Valley here. And the river takes a big turn and has deposited this whaleback form. It's formed this whaleback form, which postdates the ice sheet, but of course predates the Fraser River having cut down through this sequence to its present position. And that is a very diagnostic form. You see that, you know, on the Columbia Plateau in areas traversed by Missoula floodwaters. It's a biconvex or multi-convex form that is very, very different from a fluvial terrace. And previously, when we didn't have LiDAR imagery, these were interpreted to be fluvial terraces. But fluvial terraces are flat. They basically are inherently flat. They're not convex whaleback forms. They are flat surfaces separated by treads. And this surface dips more steeply off its ends than the river does. It is actually has a much higher gradient on its edges than the river and can really only be explained as a result of floodwaters. And the sediments kind of, to me, confirm that at this one site, that we're dealing with a flood that really filled the entire valley here. So it gives you some sense of scale because this, you know, surface is 100 meters, more than 100 meters. It's actually about 150 meters above the present day level of the Fraser River. So the waters here were quite deep and they extended right across this valley to the East Valley wall. That right away told me that we're dealing with very large discharges, you know, orders of magnitudes larger than the present day discharge of the Fraser River. And here's another site. Now this one's a little farther north, north of the town of Lillooet, but still in the Fraser Valley. It's near a place called Pavilion. And again, the LiDAR imagery just yells out to one that this whole area has been sculpted by floodwaters. This is not glacial sculpting. This is sculpted by waters. These are convex ridges. In the exposures, these neat exposures along the edge of these landforms, you can see this remarkable flood sediment. You can see it's kind of very poorly sorted. We call it a diamicton or a gravelly diamicton, a mixture of everything from silt up to boulders with large rip-ups of till. The red things in there, the brownish red things are till that have been picked up by the floodwaters and carried kilometers away from their source down valley. In addition, on the surface at sea here, we have these very large blocks of basalt that were transported by floodwater. They lie on a terrace. They cannot be glacially transported. They actually postdate the disappearance of glacier ice in this area. So they have to have been transported away from their source, in this case, up in this area at the top of this LiDAR image, down some hundreds of meters towards the south, downriver. So, you know, independently, I've been studying a lot of sediments like this, and one could wonder how in the world can a block of till survive transport and be deposited in sediment like that, with boulders that are themselves up to a meter across. And the only way to do that is if the sediment is carried at the base of a flood as a traction carpet. It's almost like a debris flow, but it's what we would call a hyperconcentrated flow, where the material is rafted in a carpet of sediment so that it actually is buffered or protected by the sediments on both sides. And it's inescapable that that has to be the explanation, because these blocks that could otherwise be easily destroyed by normal transport in the bed of a river, sort of class by class, would never survive the length of transport that these have. So that's was the record that we found near Pavilion. And again, we were able to show that the floodwaters reached up to this highway here and extended all the way across the valley to the other valley wall. And to give you a sense of scale, that's about 800 feet. That white bar there is 800 feet. So that's, at least for a short period of time, a very large flow. And then even farther south of Lytton, we have these, albeit they're not as nice as the West Bar ripples on the Columbia Plateau and the Columbia Valley. They are ripples that formed at the base of a column of water that was flowing across this surface. And the material that forms these ripples is a boulder gravel. So there's a 1 meter boulder that was transported as a particle by the waters that really form these ripple marks, these mega ripples. And then way farther south, so now we're probably pretty close to 200 kilometers from where the ice dam failed, down near Yale, which was the head of navigation for the Caribou gold rush, where the Fraser River actually becomes so canyonized that they couldn't safely have boats reach farther up the river than Yale. But at Yale, and again, a Lidar image here tipped up so that you can kind of see these landforms. You can see this beautiful Whaleback ridge. You know, it's not a terrace, it's not a river terrace. It slopes off to the side. It doesn't have a sharp break like a normal river terrace would. And it slopes steeply down valley, steeper than the gradient of the river itself. And it's covered by big boulders. You can see these little dots here are actually large boulders that form a carapace on which this feature underlies. And on the opposite side of the river is another kind of another Whaleback, not as nicely streamlined as the one on the west side of the valley, and a Kettle right here. So there were blocks of ice probably that were carried by these floodwaters from the ice dam 200 kilometers to the south and hung up in this area, and eventually the ice blocks melted out to form the Kettle beneath this crude channel form that cuts across the meltwater ridge. And this is just an example of what the surface of one of these Whaleback ridges looks like. This happened to have been recently logged, so you can see the materials that form the surface or the carapace of these Whaleback ridges. And very large boulders, you know, atypical of what you would see on a normal fluvial terrace. Some of the boulders are well over a meter across and must have been moved again by the floodwaters, which here had probably depths of many, many tens of meters. And then finally, one of the last sites that we were able to document is actually in the Fraser Lowland west of Hope. So here we are down where the floodwaters left the canyon and flowed westward and southwestward across the lowland, which is expanding in width as you go westward and eventually includes the Puget Lowland and the Fraser Lowland in British Columbia. But just south of the Trans-Canada Highway, for a short period of time, and it's not there anymore, but there was this gravel exposure or this exposure that we were able to document that shows these inclined beds of sand with scattered stones in them. To give you a sense for scale, the height of this exposure is about 12 meters, and they overlie these flat-lying beds. But I attribute this event that formed these inclined beds to be the megaflood that now was in a wider valley and probably was not as deep. So the site where we see that photo is right here, and that site is right here in this image. It forms a little terrace that is kind of protected from erosion by the Fraser River by a bedrock spur. And if one extrapolates these deposits to what was probably their original form across the valley here, you're looking at a 1 kilometer wide tract of floodwaters that were likely about 30 meters deep in here. So, and traveling at a speed of many meters per second. So you can imagine the volume of water that was now on its way to the west past Chilliwack and Metro Vancouver. And then this is just another, yet another example of the value of Lidar, because I was always aware of work that Jack Armstrong, you know, a really wonderful quaternary geologist or glacial geologist has done. He produced really the best surficial geology map of the Canadian Fraser Lowland right down to the Washington border. And he showed these features, you know, these really weird features, these linear kind of ridge-like forms that splay out west of the community of Fort Langley. And he didn't really have an explanation for them. I think he thought that they might be a product of grounded ice, of ice forming lineations at its base in the substrate. But that doesn't work very well because these ridges are in late glacial marine sediment. So the ridges themselves formed after the glacier had vacated the area. So you need some other agent to erode them. And in that Andre Blaise-Stevens paper, we speculated that these might have been eroded by the megaflood when it reached the area of Fort Langley east of Vancouver. And so I was very keen to look at the Lidar of this area once it was available. And this is kind of the bare earth Lidar showing this area that was traversed by the floodwaters. Fort Langley, just to give you a sense for kind of topography in here, Fort Langley sits nested inset into these features. So Fort Langley sits on an old abandoned meander bin of the Fraser River. It's very, very low in here. It's only about 5 to 10 meters in elevation. So these features are older. They've been eroded and truncated by the Fraser River. And because they are formed in glacial marine sediments that we know are only about 13 or 14,000 years old, they have to be younger than that. So that spoke to me that they're likely are late glacial in age, because it's hard to imagine a contemporary climate flood having a flow that large that it would carve those forms. And interestingly, Don Easterbrook and Dory Kovinen, working south of the border, documented a very similar tract of forms. Matter of fact, they look identical. And they're east of the town of Linden. There's a typing error there that somebody pointed out to me. Linden's L-Y-N-D-E-N, not L-I-N-D-E-N, south of the border. So the floodwaters probably split along Sumas and Chilliwack Mountain, and one part of the flood went westward across the Langley area, and the other part of the flood crossed the border and extended across the Puget Lowland in Whatcom County. And so these features, interestingly, are also developed in glacial marine sediments. They're developed in the same unit, the Bellingham Drift glacial marine sediments, that our glacial marine sediments are. So there are remarkable similarities in form, and I would think that both are a product of this megaflood. And it is interesting, if you look at this topographic profile here along this white line at the upper image, it crosses two areas that are the lowest in the topography, the Nooksack River drainage and the modern Fraser River drainage. So you would really expect the floodwaters to be concentrated along these two low-lying, relatively low-lying paths with depths of, some tens of meters, maybe 20, 30 meters of water flowing across those valley forms. So what was the age of the megaflood? So this is, of course, of interest to me because we kind of know when Glacial Lake Fraser existed with some uncertainty, but we needed to know when the flood occurred. So we approached this in a variety of ways. One way was Andre Blaise Stevens had radiocarbon ages of the gray silty, the anomalous gray silty clay beds in Saanich Inlet. She had shells directly above the clay beds and wood shells between two clay beds, or actually two, and shells below the lower clay bed, and also wood fragments below the lower shell bed. And each of those horizontal bars is a radiocarbon age on one of those fossils. And you can see there's some differences among them. And the widths of the bars really represent the analytical uncertainties, the laboratory uncertainties that are inherent in radiocarbon dating. So we've included the 2 sigma range, the possible range on each age as a horizontal bar. You can see they extend, if you had to pick it, you'd say sometime between 12,500 and about 11,000, maybe a little younger than 11,000. That's right at the Pleistocene Holocene boundary, which is 11,700. So that was one metric. We know we knew from, or we thought from the Saanich Inlet work that these floods happened in that narrow time window from about 12,500 to 11,000 years ago. The second approach was to, and I don't know how familiar participants will be in this technique, but it's called terrestrial cosmogenic nuclei dating. And how we applied this was to obtain the cosmic ray exposure of boulders, flood transported boulders of granites and granodiorites that allow a unique isotope of beryllium tin, to accumulate in the surface of a rock, just below the surface of a rock, within a depth of about 0 and 2 centimeters depth. And over time, at a known rate, cosmic rays, solar radiation, will produce beryllium tin ions, and that accumulates in this thin crust of rock within these flood transported boulders. So over time, beryllium tin increases, and you can actually determine from how much beryllium tin there is in this crust of each boulder what the approximate exposure age is. It assumes, of course, that the boulder hasn't been moved because it's sunlight that actually produces this transformation. So you got to be sure that your boulders haven't been tipped over, they haven't been exposed by erosion, but we're pretty sure, that these big boulders, these meter-sized boulders, some cases larger, sitting on the surface of these Whaleback ridges, have been sitting there since those ridges formed. And so we got 9 ages, three sites, 3 ages at each site. They're not trivial. It costs a couple $1,000s a sample to do this analytical work. And they're shown here by the 3 bars at the bottom. And the full 2 sigma range is shown by the gray bar, and the quartile range, or the range over which likely 50% likelihood of the true age, is shown by the colored bars. And the median for the 3 samples is that thin black line. There are some differences, but again, if you kind of compare the vertical position of the TCN ages at the bottom with the radiocarbon ages at the top, it leaves you pretty convinced not only that the Saanich Inlet flood beds are indeed a product of an outburst flood, but they're the same age as the flood landforms that we see in the Fraser Canyon. And then there's another technique. As a geologist, I marvel at the way you can get a handle on the age of an event. And this argument is a little more intuitive and a little less, quantitative. It's not an absolute technique. But if you look at that image there of this flood terrain west of Fort Langley, you'll see this flat little surface up there. That's a very telltale surface, because within that surface, there's a gravel pit, and it's right there. There was a gravel excavation that showed that this surface is not again flat, but is sloping to the northwest down the river slightly. And the sediments in the exposure were Gilbert foresaid beds of a delta. So this is a delta that was built out into the sea at the end of the last glaciation, while the landscape was still depressed. And how much was it still depressed? Not an awful lot, because that surface only sits 20 meters above sea level. But the Fraser River was flowing into the sea for a very short period of time when the land was still depressed and the sea surface sat 20 meters above its present level. So when was that? Well, interestingly, we know exactly when that was. And how do we know that? Because we have a sea level curve for the area. This is the sea level curve that shows how the land isostatically rebounded from an elevation above 150 meters down to below its present position by 11,000 years ago. That's remarkable. What that's telling you is the removal of the ice sheet is causing the land to pop up like a cork. It's going like into the sky. And when was the sea at 20 meters above sea level? Well, you can measure it right off here. It's right about there. Or there, sorry, 30 meters. 20 to 30 meters. So at that time, when the sea surface was 20 to 30 meters above sea level, we have an age of just under 13,000 years. And the flood occurred after. That's a maximum age, because the floodwaters actually scour and erode that delta. So the flood occurred after 13,000 years ago. How much after? Well, we really can't say on the basis of this evidence, but I kind of think like the sea was near its present elevation, but these glacial marine sediments were still plastic and wet, because I don't think the hardened concrete like glacial marine sediments, if they were dry and well above sea level as they are today, would erode in that fashion. I could be wrong, but that's kind of a supposition. So the sea level curve tells us when that delta formed, and therefore when the flood happened, or at least provide a maximum age of 13,000 years when that flood happened. And yet there's another piece of evidence. This is interesting, the same type of argument. Jack Armstrong mapped this green blob down here near the border. It's called the Campbell River Delta. It is a very large marine delta that was built out into the sea, built out when the sea still covered areas here shown in light blue, which are his Capilano sediments, and is connected by a meltwater channel that extends across the lower image to the east, way back to Aldergrove. And at Aldergrove, there was an ice margin at that time. So the ice margin kind of connects that delta at a given sea level, 30 meters, to an ice margin that's been precisely dated, well, almost precisely dated to 12,000 years ago. So this delta is slightly higher than the Fort Langley delta that I just spoke to, and likely formed a little earlier. And we think, again, probably dates to the time when, near the time that flood occurred. The flood occurred after that, but not much after that. So that allows us to link an ice margin to a sea level position, and the sea level position as a maximum to a time when the flood occurred. So I'm just finishing up here. Interestingly, and I've often wondered about this because the Fraser River Delta didn't exist 10,000 years ago. The Salish Sea, the Strait of Georgia, extended all the way east to New Westminster, which is located in that top image right about here. And by 5,000 years ago, not only was the Fraser Delta really much advanced, but a former fjord lake or arm of the sea had been filled in the Pitt Meadows area, shown here in this yellow pattern. So there had been a huge influx of sediments between this time and this time. And I have to think, and this is a situation today, I have to think that that flood formed much of the platform on which the Fraser River was able to produce the modern feature of the Fraser River floodplain and the Fraser River Delta. It was instrumental in doing that. Okay, and then finally, the last thing I want to talk about, it's a bit of a ringer because I'm interested in all sorts of things. So I'm interested in archaeology. I'm not an archaeologist, but I love archaeology. And about a year ago, some archaeologists found on Calvert Island, which is up the coast, mid-coast British Columbia, they found footprints of human beings kind of in mud, preserved in mud, buried in younger sediment. And they were able to excavate those footprints, and nobody doubts that they're footprints. It's a group of people who were standing in a muddy area, and their feet left imprints in the mud. And beneath the imprints, or within the imprints, are fragments of datable material. They actually had bits of charcoal and wood and leaves of plants that they were able to radiocarbon date. And so they came up with ages that are 13,000 years or a little older. And why am I pointing this out? Because I've often wondered if people were present in the Fraser Lowland when this flood occurred. Were there not only flies on the wall, were there people that were actually impacted by this flood? And my answer is likely, that this flood did actually impact the coastal peoples who we know were there shortly after that. We know from excavations in the Fraser Canyon in the Metro Vancouver area that people occupied those areas 10,000 years ago. But I think they were there before that, because why wouldn't they be? People were on the Central Coast, and even more recently, a site in New Mexico has been documented with human footprints that date back to more than 20,000. So people were not only present here at the end of the last glaciation, they were present in the continental United States more than 20,000 years ago. This is a paper that was just published in Science, and it's really overturning ideas about the timing of human occupation of the Americas. So to me, it's kind of, when I think about this and its significance, well, actually there were people that probably witnessed this flood. And there are lots of flood stories, of course, in indigenous oral cultures. It's hard to attribute them to one event, but here's probably a great example of one that they would like to pass down from generation to generation. So with that, I'm going to close. And I'm happy to, I don't know how you want to handle it, Dale, but if you would like to open it up for questions, I'd be happy to, or comments, I'd be happy to do that. I'm going to stop.
Well, thank
sharing.
you, John. You know, I think the easiest way for us to do questions might be for us to all open our chat window. And I saw some questions put in the chat during the presentation, which are still there. But to facilitate hearing the questions, if everyone would open that chat window on the bottom of their screen, kind of in the middle of the toolbar, it says chat.
Yeah.
And John can start by looking at the questions that are in there, and then additional questions can be typed in. Let's try it, see if it works.
Okay. I see one right at the top. Let me see, maybe I should make sure, work my way down. Okay. We can't see the screen. My fault. Any evidence of floods in interior lake deposits? I'm not sure interior lake deposits. We don't see floods so much in these glacial lake deposits. And I'm not sure what the question is driving at, but it did cross my mind that there are lakes that are positioned in the Fraser Valley at elevations where they should have been impacted by a flood like this. And, you know, if I were much younger and starting my career, I would probably be targeting those lakes for coring to see if I could find influxes of flood sediments at the time, you know, at this interval between about 12,000, well, around 12,000 years ago. And I've got a couple of target lakes. Kakawa Lake near Hope, if you know that, is a good target lake. It's about at the right elevation. But it's not a trivial undertaking to get cores of that transition. You know, it's often easier to core through these organic rich muds, but once you reach coarse sediment, you often get rejection. So I don't want to be rejected at age 75. So I don't know if I answered that question. If not, just pop another comment in. Yes, the till masses could have been frozen during transport. That's possible. That's possible. The climate still would have been kind of a glacial climate because it happened when there was still substantial ice cover over the coastal mountains. It wouldn't have been the climate we see today for sure. So that's one way of getting these, as you remember, these kind of pinkish, purpley till class to be preserved during transport. But I still think, you know, given the likely erosion of your classic flood, your clear water floods, that probably isn't the mechanism by which they're transported. Okay, and then there's a question, is there evidence of multiple Fraser floods? That's an interesting one, because in the case of the Missoula floods, you know that Dick Waite and Brian Atwater and others have argued that there might have been as many as 80 during the last glacial cycle. Here, no. I think that there may have been two. In Saanich Inlet, we see evidence for two events, closely spaced events. And I haven't really talked about it, but it's possible that the Glacial Lake Fraser reformed after the initial breach, the big breach, and that there was a second event from Glacial Lake Fraser. Or it could have been a flood that came from another source. There's other possible sources for floodwaters that might, say, reach Saanich Inlet, where we seem to see evidence for two events. But two at most, you know, there's no evidence in the Saanich Inlet cores for more than two events. And part of me wants to say that, you know, it's kind of a little bit different situation because the ice sheet, this flood or these floods occurred after the Missoula floods. They're not long after the last Missoula flood, but they're after. So the ice sheet essentially had retreated north of the Clark Fork River and no longer could impound Glacial Lake Missoula. And in fact, the ice sheet was on its last legs. So I think that the ice sheet, rather than re-advancing as it might when it was much more healthy, was actually continuously retreating. So that once it kind of retreated past blocking the Fraser River south of Williams Lake, it wasn't going to do it again, or at most maybe one time. It just didn't have enough kind of oomph to reform a big lake. It was a kind of a one-off event. What we need to know that possibly could be determined, because my research has just set up a whole bunch of other possible research programs, is were there other sources of floods in interior valleys in BC? Did Glacial Lake Thompson, remember I showed you the white silts in the South Thompson Valley, could that lake have drained catastrophically? And it would still have to go down the Fraser Valley, and you'd think you'd see evidence of it, which I haven't seen, but I wouldn't totally rule out that as a possible source for another flood. Okay, another question is, when the deposits approach sea level of the time, one would need to model sea level versus global eustacy against glacial depression rebound. Have you modeled this for the Fraser River Delta versus up valley deposits that might have been submerged back then? Well, that's a very good comment. Thanks very much, Paul. I appreciate that. Because what we found is we've done a little bit of modeling, but kind of that glacial isostatic response differs over very short distances. And we think that's partially a function of the fact that the ice sheet was sitting on a low viscosity mantle. In other words, of quite a soupy mantle. It had a viscosity 2 orders of magnitude lower than the mantle beneath Hudson Bay. So what that means is over very short distances and over short periods of time, the rebound can differ and differ substantially. So that's an impediment to kind of at least understanding in a quantitative way, how that rebound might have played out from west to east, from Vancouver east into the area around Chilliwack and Hope. And so the short answer is no, we haven't done that. Tom James, who's a glacial isostatic modeler, has done kind of the preliminary work on the impact of the subduction zone, the low viscosity mantle, the high heat flow on the pattern of glacial isostatic response, but we don't have good data sets once you get very far east of Vancouver. We lose evidence for the exact position of the sea surface over time. Once we get east of Vancouver, we just don't have those records. And I think way more could be done. Trying to get Tom James would have to step up to the plate, because it's sort of beyond my level of ability to do that sort of thing. Okay, and I see another comment. Can you recommend 1 or 2 good books or technical papers that cover this flood? I published a paper on the flood, and it's in geomorphology. What I can do is I can send it to Dale, and anyone who wants it could get it from Dale. So it was published in the journal Geomorphology about 8 months ago, and it kind of summarizes this story completely. And I'll also send to Dale that paper by Blaise Stevens, because that's the one from Saanich Inlet kind of set the stage for this study. To me, it's a 40-year kind of journey, and I'm not done yet. I'm still kind of interested in following up on some of the loose ends, but really what I wanted to do was get it out there. And it changes the way we think about the sedimentary architecture in the Metro Vancouver area, because in my view, that event had to leave a significant deposit below the post-glacial the post-glacial alluvial deposits of the Fraser River and the Fraser Delta. And I think maybe it will require some reinterpretation of the significance of the deeper deposits. And the deeper deposits are increasingly coming into play with the major infrastructure projects that are happening in the Metro Vancouver area. There's a big push now to improve the water distribution system. All our water is surface water, and it comes from reservoirs in the coastal mountains north of Vancouver. So it's carried by a large distribution system to the growing communities south of the Fraser River, including Surrey and Langley. And there are multi-billion-dollar projects that are in progress now that entail deep drilling and understanding the three-dimensional geometry of the glacial fill in the Metro Vancouver area that I think kind of need this information, or it needs, we need to kind of open our eyes to the possibility that a catastrophic event is controlling some of the subsurface geology in the Metro Vancouver area. So I will definitely do that. And Art and Sharon, if you want to touch bases with, because I don't have your contact information, but I'm sure that you do, Dale, probably, I'm thinking. But you could make those papers available once I send them to you.
Definitely.
Okay. See. Yeah, all the point was, John, you mentioned many C14 ages. Yeah, they're all calibrated. So all the Saanich Inlet ages were calibrated at the time using, I think, the Caleb system from the University of Cambridge. So there, I was referring to not raw radiocarbon ages, but calibrated ages. And the surface exposure ages, the TCN ages, are also, they're not calibrated. They're simply calendric ages. That's the way they're expressed. So you'd have to calibrate the radiocarbon ages to make them comparable. Oh, Ralph. Hi, Ralph. I didn't know you were there. In Whatcom County, Dory, Don, and I estimated the flood occurred when relative sea level was 12 meters at Dellingham, rising to the north at about 3 meters per kilometer. That sounds pretty reasonable to me. Pretty reasonable. Yeah, if you extrapolate that, my delta at Fort Langley is at around 25 meters. And so the sea surface, when that delta formed, would have been pre-flood, but not much pre-flood. So it was sort of in the right ballpark, I think. I see Kathy's there. I haven't seen Kathy in a long time, but it's great that thanks, Kathy, for joining in. And do you see any evidence for Easterbrook's yo-yo tectonics north of the border? No, I don't. And matter of fact, that's always been a source of disagreement between Don and myself. And I would defer on that point to Doug Clark at Western Washington, because he just published a paper in a GSA collection of papers honoring Steve Porter, a summary of kind of a reinterpretation and at least an alternative interpretation of the lake glacial geology just south of the border, and kind of arguing that the size of the resubmergence was not as large as Don thought. Don and I and Doug are really in great disagreement over this and have been for a long time. North of the border, there may have been a little resubmergence, it's possible, but not of the order of 100 meters, which I think is what Don was arguing, as I recollect. Okay, the next question is, any linear features in Lidar that could be tectonic in the lower Fraser River Valley? Boy, we've been looking, I tell you, all you Americans who are documenting all these active faults south of the border is so cool. We haven't seen anything that we yet believe to be neotectonic in the lower Fraser River Valley, which may seem kind of surprising because there's a beautiful fault, with multiple ruptures on it just south of the border, south of Sumas. We've been looking and we just haven't seen anything. Having said that, there's a group of researchers who identified 3 active faults now on Vancouver Island, or what they think are active faults. And one of them quite clearly is, and this is the Leech River Fault that extends across the north end of, well, it kind of in that Gulf Islands area off Victoria, across over to, I think, Whidbey Island, and is connected to that. And then the same group has documented an active fault paralleling the spine of Vancouver Island, but west of the spine, near the city of Port Alberni, which is an active fault. And then recently they've identified what looks like a recent fault rupture in Victoria near Elk Lake, Elk and Beaver Lake, which is on the peninsula just north of Victoria. So I wouldn't rule out the possibility that there are Holocene active faults in the Canadian Fraser River lowland, but we haven't seen them. And now we have full LiDAR coverage of that area, which we're continuing to look at, but I don't know, maybe it's just been so kind of greatly developed that, the evidence is not as strong as it might be at some places in the Puget Lowland. I don't know. We're still, I would hesitate to say that there aren't any. I would definitely not say that because of all the evidence that has been gathered south of the border, that you've got this tectonic regime that should extend up to the southern end of the Coast Mountains. And you would kind of expect there to be some slip along faults, even old faults that are favorably oriented beneath Vancouver. Are there similar flood stories on the east coast of the United States and Canada? I don't know. That's a good question, Mary Lynn. I don't know. I know that there are ubiquitous kind of flood stories on the West Coast, but some of them, many of them seem to be linked to Cascadia subduction zone tsunamis, particularly the last one in AD 1700. And it's interesting, flood stories, if you really look at it globally, they're quite common in ancient cultures. And it's hard to know what to make of them often. The kind of the biblical flood seems to appear in very old kind of stories from the Middle East. And, the flooding of the Black Sea, people have made varying interpretations that those are actually passed down from generation to generation. It's interesting to think about, but it's very hard from the nature of the stories, which are exaggerated so that they can be carried from generation to generation, just exactly what was going on. Particularly these Cascadia tsunami stories. Man, if you had a tsunami story that ran up to Mount Aerosmith, which is kind of what the indigenous legends propose, that would be one heck of a tsunami. Mount Aerosmith is like 5,000 feet high. But how else are you going to pass a story down unless you kind of exaggerated a bit? That's kind of the way I feel about it. There's some substance to those stories, but exactly what the floods were is an open question.
Well, thank you, John. I think we've come to the end of the questions. Did I miss one? I think that's about it with the questions, and a lot of comments thanking you for an excellent talk. And I, of course, would second that. We truly appreciate your willingness to come and speak with us. And we always enjoy having you, and man, a lot of things to think about.
Yeah, well, I wish I could be there in person, you know, still,
Well,
still
maybe
being
next
edgy
time.
about travel, but it's coming. So
Yep.
I thank everyone there. I see few names, few people I know, and thank you very much for each of you for kind of tuning in on this. And everybody take care. And hopefully the border's a bit more open now, and I hope to see you sometime.
And let's all give John some reactions with the reaction button down there. You should be able to hit that and give him a round of applause electronically.
You gotta love Zoom.
You got to. I see Art and Sharon are giving him the video version. So anyway, thank you, everybody. Thank you, John, and have a very good evening.
You too. Okay, thanks all.